Okay, a few words about the so-called unreasonable effectiveness of mathematics. Um, this was the phrase coined by Eugene Wigner, and it's something that people have, scientists in the tradition of Wigner, which you might call the popular post-war tradition of physics. This is something that those scientists have appealed to repeatedly. As a matter of fact, a few years ago, I had occasion to talk to an eminent physicist from the next generation of scientists over here and ask him to explain this particular concept in the context of general relativity. You see, when I first encountered Wigner's phrase about the unreasonable effectiveness of mathematics, it was an excerpt from his writing, something about the power of mathematics is something that we neither understand nor deserve, which is what Wigner said. And this remark was inscribed on a board at the Institute of Mathematical Sciences, where it was at the entrance to a long corridor with walls decorated with various pictures and artifacts from the institute's history, letters by Heisenberg and Bohr framed and hung on those walls. And right below Wigner's remark is the compressed version of Einstein's field equations. And in any case, I was curious about the actual applicability of Wigner's observations in that article to what Einstein achieved with general relativity. This particular scientist with whom I had consulted had written an introduction to a local edition of the Feynman lectures, and he said that perhaps one of Feynman's most important contributions is bringing people's attention to this so-called unreasonable effectiveness of mathematics, and in particular, in his Feynman's series of lectures, The Character of Physical Law. In any case, I pressed this very eminent scientist on this point and said, well, general relativity involved the invention of a little new mathematics, that is, the Einstein summation notation was devised for the purposes of general relativity. So in that context, how conceivable is it that Einstein would have been able to frame his field equations, the ones inscribed under Wigner's remark at the Institute? How plausible is it that Einstein would have been able to frame it had he not invented that mathematics himself? Had he taken it for granted that he would have recourse to use existing mathematics to complete his formulation? And the scientist very correctly pointed out that the summation notation is perhaps just a minor contribution to the underlying mathematics of general relativity and of course the field equations more generally, more exactly. The bulk of the mathematics had existed for decades before Einstein began his work. So you think about the history of non-Euclidean geometry. You have Riemann and Christoffel, to some extent Gauss and others. And all of this existed well before Einstein picked them up and used them for general relativity. And this is quite a satisfactory explanation. The problem was with my question, really. Had I pressed him in the context of classical mechanics, in particular in the context of Newtonian mechanics, then the answer would have been less straightforward. You see, Einstein's summation notation is regarded as a great innovation in a certain tradition of mathematics, a certain tradition that maintains that any advance in mathematics consists in a invention of new notation. In fact, this is actually at the core of the dispute between Newton and Leibniz. So, historians are altogether undecided as to whether Newton or Leibniz deserves more credit as the inventor of calculus. If you accept the premise of this tradition of mathematics that notation is at the base of a theory, the invention of a new notation is at the base of a theory, then Leibniz would have to be given credit. Most of the notation we use today in calculus was Leibniz, was invented by Leibniz, not by Newton. We use occasionally Newton's notation for the derivative of a function of time, but not much, not otherwise. Besides, Newton deserves credit if you reject that premise and you say that a serious, well, any particular idea in mathematics constitutes a serious advance if it produces, serious insight into the world we live in, or into the existing problems with which man is generally concerned. In that sense, if you accept that premise, then Newton deserves more credit. So that's at the core of the dispute and notation. So if I had pressed him with the example of calculus, then he might not have had a more straightforward answer, and I was foolish for not having taken that up. Because you see, calculus was invented in order to produce the existing formulation of classical mechanics, more accurately, Newtonian mechanics, right? Newton needed a body of ideas, a body of methods and procedures and modes of analysis with which to proceed, with which to frame his discoveries, his convictions, and the various computations he had performed with regards planetary motion and the motion of everyday objects. And calculus came out of an effort to create this basic framework. If you take a look at the Principia, he says that the goal of the Principia, which is actually the goal of modern of what we call classical mechanics, is, according to Newton, to cultivate mathematics so far as it regards philosophy, meaning extend the existing universe of mathematical ideas so that it becomes capable enough of discussing the problems of the real world, of the universe in which we exist. And here you see an anomaly. Actually, that particular scientist admitted that the invention of the Einstein summation notation does constitute an event defying the general pattern in which physicists have the choice to just look at existing mathematics and apply it. But he says it's an anomaly, and that's true. It is an anomaly. More often than not, physicists do not have to invent new mathematics for their theories. But in this sense, Newton's work is an even greater anomaly. And then you might also argue the same is true of Maxwell. In fact, the same might be said quite reasonably of most of the scientists who concern themselves with the really serious questions. That is Newton, a few centuries later Maxwell, to Einstein, and a lot of and innumerable examples in between. But Wigner does have an additional context in which he discusses the so-called unreasonable effectiveness of mathematics, and that is something that is less easily done away with. In particular, he wonders how it is that mathematics that was invented by humans for humans as an expression of purely human creative energy could possibly one day come to be seen to reflect something in nature. This is a question that has troubled philosophers since the beginning of recorded history, possibly, and recorded human history, I meant to say. I'm sorry. And in the context of Wigner's own interest, quantum theory, you can see what happened. The foundational document of what's called non-relativistic quantum theory and what was initially called wave mechanics was Schrodinger's series of 6 or 7 papers, which all had the same title, quantization as an eigenvalue problem, part 1, part 2, etc., up to part 7. And in these series of papers, Schrodinger repeatedly quotes or makes reference to a single technical text. More than any of the other citations in these papers, he several times cites a textbook, a mathematics textbook by David Hilbert and Richard Courant, Hilbert and Courant's mathematical methods for physics. And it would be interesting to see if there is any other paper from that period, the mid 1920s, which so extensively cites a textbook as its source material. And in any case, a little investigation into the history of this textbook will show you that it was deeply reviled before Schrodinger's paper came out. It was reviled by physicists for containing so many ideas that should be purely of interest to mathematicians and of no interest to physics. Ideas such as perturbation theory and the treatment of differential equations as eigenvalue problems and other related ideas. These were considered, completely abstract, full of the ideas rich in symbolic manipulations that mathematics and in particular algebraists so deeply enjoy, and having nothing to do with physics. And then along comes Schrodinger and says, well, we might, David Hilbert might have invented those things out of a pure need to express his inner creative energy, but it actually does seem to reflect reality in the following way. That is, the spectra of radiation emanating from various substances seem to follow patterns that can be described accurately or modeled accurately using the methods that Hilbert put forth. So that is the limited context in which Wigner was talking about the unreasonable effectiveness of mathematics. But you can reach as far back as you want, and you'll find this question being explored. If you look, if you go back a few centuries, you see that Kepler, in taking the data of his mentor Tycho Brahe and attempting to find a model upon which to fit the data, began using Copernicus's idea that the planets follow circular orbits around the sun. And then when that failed, he made just a slight modification to his theoretical model. He said, well, perhaps the planets follow elliptical orbits around the sun, and that turned out to be correct. Centuries later, Einstein would look at what Kepler did and said, well, Kepler was great because he made the following guess. He guessed that ellipses, an imagined geometry object purely of concern to humans, which had been occupying human interest for centuries because it derives from a certain line of investigation into geometry. He guessed that these objects might in some way reflect, have something to do with the world in which we live in, even though they were, that is in a sense deeper than simply human beings projecting them upon the world from their imagination. Kepler is great, in effect, what Einstein is saying is Kepler is great for having related the natural world to something that human beings have, to human imagination, to an element of human imagination. And in fact, Kepler is a relatively recent example. You can go all the way back to even 2000 years ago to find this question being explored in the philosophical works of the ancient Greeks and in all civilizations that flourished at the time. So yeah, that's my 2 cents on the unreasonable effectiveness of mathematics. We can discuss a lot more about it. We haven't begun to scratch the surface. If you want to, head on down to the Centaur Courses and I'll see you there. Okay.